when we come across certain logarithms, you know, if I've got logarithm base 5 of 625, that's a nice logarithm. I can figure out what that is. 5 to what power gives me 625. That's a nice power of 5. It's fourth power, right? And so, yeah, figuring out that logarithm, I can go through the basic definition and figure that out. Now, if it's log base 5 of 500, though, the problem there is with using the definition, 5 to what power gives me 500 is, that's not a nice power of 5. You got 5 to the third is 125. 5 to the fourth is 625, so I skipped right over. Best probably doing it this way. Doing it this way is I could say, well, it's probably closer to 4 than it is to 3, right? Because I need 500 out of that, but it's 3 point something, right? That's probably what I could get out of doing it with this definition. Well, the change-of-base theorem allows me to figure that out a little more precisely, accurately, or to get an actual number here for this. Okay, so here's how it works, and I'll just, if I have the log base A of B, I can evaluate that with this change-of-base theorem. And you can use any base you want. Log base A of B equals the ln of B over the ln of A. And I choose, over here I choose, so you see why it's called the change of base, because I've changed from base A to base E here. You can do this for any base. I just happen to choose base E here because that's a lot of times the logarithm that we prefer to work with, logarithm base E. But I could do common log the same way, make it common log B over common log A, log base 2 B over log base 2 of A. I could do any logarithm, change any base I want to using this. So it's ln of B over ln of A. Now, this, where does that come from? Let me, we'll use this here in just a second. I'll just show you here where we get this. So we got the log base A of B, and I'm trying to figure out, call it Y, what that equals. But if I look at that, that's kind of a log equation. So if I use the, if I exponentiate both sides here, make it A to that equals A to that, that, using the property, cancellation property, that gets me B equals A to Y. Then, ln both sides. That Y pops out. And so Y is what the value I'm looking for. So if I solve that, divide both sides by ln of A. Divide, because that's times ln. Just divide both sides by ln of A. So yeah, we've got Y equals log base A of B, but Y also equals this ln of B. So these two things are equal, you see, which is exactly what I've got here. So that's one way you can see how this works. All right, so let's, really what we're interested in is applying it. So back to this one. So what is the log base 5 of 500? Well, if I take, by the change of base theorem, what would it be? Well, the change of base theorem says take the ln of B, this is B, this is A, take the ln of B, 500, divided by the ln of A, which is 5. And now we can use, calculators, most scientific calculators are equipped to handle that. ln of 500, divide that by ln of 5. 3.86, how many ever places you want. 1, 3, 5, or up to the ones you got displayed there. Yeah, and we said, it's probably closer to 4 than it is to 3, and sure enough, it's about 3.86. So that'll work on any logarithm we can't figure out. Now, on the test, I will still want you to be able to do definition-wise, be able to figure out logarithms. But this gives us a way to figure out logarithms we can't usually figure out any logarithm we want. So if I've got log base 7 of 89, well, that's obviously one wouldn't be able to get. So yeah, you just do the change of base and the ln of 89 divided by 7. Gives me a way to figure those out. .30670. How many other places we want there? Okay? This is all right.